You take your current probe, it has the hole here, and you go directly to your signal generator, removing the small box that is here. The small box is the terminating the characteristic resistance. You use it not as a current transformer, but as a voltage transformer. Voltage on this side, and you have a voltage across your piece of wire. That's very funny. When you measure it the first time, you see a piece of wire, and you see a voltage across it, because this piece of wire passes through a hole is just a secondary winding of a transformer. This method works, it's used, it has only a small drawback, that the turn ratio is 275 to 1. The voltage you get over here is really small. Don't even think to open the current probe and remove some turns from the winding side in order to improve the turn ratio. There is a different way to solve this problem. If the voltage that you inject is too small, either you reduce the number of primary turns or increase the number of secondary turns. Can you do it? Sure. Because what you can do to increase the voltage you inject in your circuit is just your wire pass through, comes a second times 2, comes a third times 2, comes a fourth times 2, and then you fill the windows on the space, no more room for more turns. But you can have 4 or 5 turns on the secondary side, so your output voltage goes up by a factor of 4 or 5, whatever, how many turns you put. This is the easiest way to do it. And does not require too much burden, because you just cut, even if you have a PCB, you just cut a trace with your PCB, you solder a piece of wire, and you clamp it with your current probe. Very easy, even if you already have a PCB prototype, etc. Okay, so that is the first way. We will use it. You will use it in the lab. Oh, by the way, I put online a couple of days ago the instructions for the next lab, Tuesday lab, doing exactly this. So you will have to design a circuit with one op-amp that gives you the behavior of a power stage. It could be a buck or a buck boost. There are the specs on the file I put online. Then you have to add to design the compensator. That is another op-amp with a few components around, and you will inject this signal, your VZ, using this probe or using a second method. And the second method that you can use for injecting the signal into your circuit is using an adder. You use an adder and you can inject it like this. Instead of placing here your current probe used backwards, you put here just an adder with 2 inputs. This is the input 1, this is the input 2, and this is the output. Circuit adder. Don't write down a couple of lines in C just to make this addition, because it does not work. That has to be a circuit. So this is VC. If you have here an adder, what happens is that even if you don't put any VC over here, the loop is still closed, because some voltage plus 0 equals some voltage, the same voltage. So your loop is closed in DC and AC, and you can add this extra signal. And if you add this extra signal, you will have here something like VY, here you have Vx, and you inject VZ over there. Do you know how to make an adder? Oh, this adder must have gain 1 from this input to this output, because you don't want to increase or decrease the output signal. You want to pass your output signal without any change and adding your VZ. You know how to make an adder? Op-amp and 4 equal resistors. Your adder is something like this. 4 equal resistors means R, 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 R. This is we add, we sum. And if you come from here, what do you get? You get R over 2 multiplied by 2. And so we sum equals V1, V1. And then what do we need over here? Plus Vz. And how do you make it plus Vz over here? Well, you should add another resistor over here, then you have to change this ratio. It works. But what happens if instead of plus Vz you have over here minus Vz? Does it change anything? No, because Vz is out of your result. You divide Vy divided by Vx and Vz cancels out. So you can add over here Vz on the negative side. This comes from your signal generator. And here you get Vy, no, Vx, here you have Vy, and Vy divided by Vx still gives you your look at it. This works down to the DC, not like a transformer, but this works only for small voltages. Vy is your output voltage. And if your output voltage is 5 volts, 10 volts, or something like this, it works. If your output voltage is 500 volts, not going to work. You have to use the previous method. This requires one op-amp, so it means that if you design a switch mode power converter for manufacturing, you cannot add one extra op-amp to each circuit you sell because you want to measure the loop gain. Loop gain is only measured on the prototype. So the prototype you can have this op-amp, you can provide this op-amp in the PCB because it's just a prototype, but for the final version you have to remove it. That's stupid to sell one extra op-amp useless. On the boards we use in the lab, there is this op-amp. Because those are not the final product, those are just prototypes, they are just circuits to work on to see the methods of measuring, but it's not a system that you can sell. This is just for test, diagnostic tool. Okay? This op-amp usually is not too bad because it has a very wide bandwidth, wider than what you want to measure. The input impedance is not too large, so you don't load your power supply. Here the output voltage is very low, so you satisfy the mismatch, the impedance mismatch. And you can go down to DC. Next week you will have to mount on a breadboard one op-amp emulating power stage, one op-amp being the compensator, and one op-amp with 4 resistors around that are these adders. So far so good? Those are the 2 main methods to inject a signal. There are 2 more. One is if you have a floating signal generator, you can use it. But a floating signal generator is a very specialized piece of equipment. It's a very specialized tool. It costs a lot. In the lab we have maybe one, and we don't use it basically because it's just very complicated stuff. And there is nothing really isolated because an isolation means usually low frequency isolation. Then there are parasitic capacitances. And And there is a fourth method. This is a challenge that I gave my students every year for many years. Then we stopped. And is let's try to make a transformer using op-amps and respecting exactly the satisfying exactly the equation for a transformer. That means you emulate the transformer with op-amps, and it must work exactly as a transformer, with the ratio, etc. Making a half transformer is easy. Basically, power added as a half transformer. But making a real transformer, at least loading on the output, is not so easy. And I challenged students many times with these problems. And after many years, one student came out with a solution. Tried to figure out a solution. It was not working, but we fixed it, and probably it was working. I'm not really sure it worked. We tried in the lab, it seems to work, but I'm not absolutely sure. It's just an exercise, if you like, of amps and circuit electronics. Okay, this is the injection. Now, what else do we need for our system? How to inject the signal, and the second problem is how to measure Vy over the xp equals negative Vy over the x. That means you have two voltages, and you want to measure the ratio of these two voltages. These two voltages are sinusoidal voltages, so you have to find out the amplitude of these two voltages and the phase of these two voltages. They gave me the phase and amplitude, because T is a complex variable. Okay, let's start with the Riemann solution. Riemann solution, you have to use a so-called low frequency network analyzer. And the low frequency network analyzer has three connections. There is an output signal, generated by this one, is a sinusoidal signal on a frequency that you want. It can span over a frequency range. And you have two inputs that are called A and B, and one will be Vy, the other one will be Vx, and you connect your system, your circuit, your network analyzer to your circuit. This network analyzer generates Vz. How do you couple Vz to your circuit? Well, you can use an adder, or you can use a transformer, current probe. You inject this Vz into your signal, and you go with the two probes to get the Vy and the Vx. And this automatically starts from a lower frequency, goes to a high frequency, low frequency to high frequency, and makes many different measurements. And every time, for each frequency, measures the magnitude of these two voltages and gives you the ratio in dBs. Measures the phase difference between these two voltages and gives you the phase. And you get the graph, you get the table, it's very convenient, etc. The only problem is that this costs at least $10,000 or more. It depends on what instrument you get. If there are small network analyzers for power electronics, they cost, I think, around $15,000 or so. Not so expensive. And there are other general purpose network analyzers, like the one we have in the lab. It costs probably $14,000 or so just to measure it. We will use it. That is the Riemann solution. Second solution, okay, you have to measure two sinusoidal voltages to check what is the amplitude, to measure the amplitude of these two sinusoidal voltages and the phase difference of these two sinusoidal voltages. Give me a solution. Scope. And the scope is the tension-Mann solution. Because with the scope, you can measure the amplitude, you can measure the phase difference, but you set a frequency, you go to count the divisions on the screen, and to make your calculation, you go to count the division on the horizontal axis to find out the phase difference. It takes a long time. For one frequency, and then you step to the next frequency, and you repeat the procedure, and then you step to the third frequency, and repeat the procedure, and if you want to go from 10 Hertz to 10 kilohertz, well, see you in 2 weeks. The scope is very convenient, very nice, it's very good, easy to use and quick to use to determine the crossover frequency. Because at the crossover frequency, how are Vy and Vx? Crossover frequency means the magnitude of T equals 1. That's the definition of crossover frequency. So Vy and Vx have the same amplitude. You set the scope with the same sensitivity on both scales, and you go up in frequency until the two sinusoidal voltages are the same amplitude. That is the crossover frequency. Piece of cake. You see, you measure the phase difference between these two sinusoidal frequencies at the crossover frequency, the two sinusoidal segments at the crossover frequency, and this phase difference is your phase margin. Because the phase margin is the distance between your phase shift to 180 degrees. But we have one extra 180 degrees over here, and so the phase difference that you see on the scope is exactly your phase difference. This is your phase margin. It's okay for the crossover. It's not okay if you have to take hundreds of measurements. Those are the two main ways to measure your movement. There are two more that are vector voltmeter a vector voltmeter is a voltmeter that gives you the amplitude of signal and the phase of that signal with respect to a reference. Did you ever see them? It's a quite old instrument. I mean, you don't buy a new instrument like this. You buy a spectrum network analyzer because it makes more than this. But if you have only a vector voltmeter has two readings displayed, one for magnitude, one for the phase, and two inputs, measurement and reference. Reference is just to give the frequency, and the vector and the measurement takes the voltage at this frequency and gives you the magnitude and the phase with respect to the reference. Switch mode power converter has a lot of noise, really a lot of noise. You already saw it. A vector voltmeter is a selective voltmeter. It's also called selective voltmeter because it measures not all the voltages that go into the input. It gets only a narrow bandwidth around the measurement frequency, and it measures only this amplitude. So you can get rid of your noise like this. Not used quite often anymore because nobody has a selective or a vector voltmeter anymore in the lab. There are more flexible instruments and more expensive too. The last one that is just was used probably at the beginning of this stuff, the 70s or so, but just to remember your basic high school method, you have DC over here, and DC could be this one, the A, Y, and the X. Okay? If you have a scalar voltmeter, that means a simple voltmeter that gives you the magnitude and nothing else, you can measure the X, the voltage over here, you get, for example, 3 volts. You measure VZ, you get, for example, 2 volts, and you get, you measure Vx, you get, for example, 1.2 volts again. So you have 3, 2, 2. Is it possible? Then you have 3 volts over here, 3 volts over here, and 2 volts over here. Yes, sure. Which way? How is it possible? Because 3 plus 5, 3 plus 3 is 6, it's not equal to 2. Those voltages are sinusoidal voltages, sinusoidal waveforms. And here you have only the magnitude, you don't have the phase. So, what you get over here is that you have one voltage, a sinusoidal voltage, you can represent with a phasor, that is magnitude 3. A second phasor over here, that would be over here, because we add it, that is 3 as an amplitude, and the third one is this one, represented 2. Okay, you have a triangle with 2 sides that are 3 and 3 length, units of length, and the last one is 2, yes. And you want to find out the phase difference between these 2 quantities. And the phase difference between these 2 quantities is this vector. So the magnitude is measured immediately. It's 2 and 3, so you have the ratio of the magnitudes. And the phase is given by solving this triangle. You know how to solve this triangle? Say yes. Yes. Which way? It's not a square triangle or you have 3 sides, you have to find one angle. Go back to your high school, you studied it. Carnot theorem, sure. Okay, so far so good. Oh, I made some assumptions, implicit assumptions that nobody complained about. I told you, here I put my voltage source. And the voltage source I represented here like this, we see. Do ideal voltage sources exist? No, any voltage source has an impedance in series with it. So we have here an impedance Z. Does it change anything in my circuit?
There's no current here.
Oh yes, there is current. If you remember our initial circuit, there is a current running through it. The current is Vx divided by R1. And Vy, what is Vy? How did we derive Vy? Vy was equal to 8 times Vx, with the negative sign, minus R naught times Vx divided by R1. Yay! Even if there is this Z impedance in my mesh, my measurement is not affected by it. Even if I use a real voltage source that has a series impedance, an internal impedance, what I measure, Vy and Vx, does not depend on this impedance. So don't worry about it. But there is a funny part, interesting part, I used only once in my life, but I was very happy to know it. This stuff. Let's suppose that you measure your power supply and, as usual, it oscillates. It's unstable. Oops. R1, R0, Vx, it's unstable. And if it is unstable, it means that you have an oscillation whose amplitude is going to bang against the limit, against the rails. That means your system is not linear anymore. And if it's not linear, if it is oscillating, you cannot take any measurement. But if you try to make a measurement of this system that oscillates, this impedance can stabilize your circuit. Because if this impedance is large enough, the loop gain with Vz, while you measure it, your loop gain is not anymore R1 divided R1 plus R0 times n. You remember the original loop gain was A times R1 divided by R1 plus R0. If you have this accuracy, the loop gain while you are measuring, not in general, but during your measurement, your loop gain, your actual loop gain, not what you measure, but the actual one, is plus Z0. Plus Z. And so it means that your loop gain goes down. If you put here a Z large enough, your loop gain goes down. And if your loop gain goes down, any unstable systems eventually will stabilize. Once that you have stabilized it, you measure this voltage and this voltage, V1 and Vx, and you get your loop gain without the Z. So you can introduce Z, add Z, it stabilizes your circuit, you measure it, you measure the loop gain that does not have Z in it, and you discover why it is unstable. With this method, besides measuring loop gain, you can also measure the gain of each single dot, the power stage of the compensator, and you will see in the. Okay, see you on Tuesday.